Iterative BST search. In this lecture, we are going to look into how to write an iterative algorithm for searching in a binary search tree. In the last lecture, we already saw how to search in binary search tree. We also saw the recursive algorithm for searching in binary search tree. Why are we specifically looking into iterative algorithm? What is the importance of iterative algorithm? The reason is generally in all tree problems, it will be easier and more intuitive to write a recursive solution because when you are calling the same function again, many times it will look more intuitive and it will be easier to write as well as to understand the algorithm. But the iterative algorithm, it sometimes saves you some space. For example, in this particular algorithm, BST search, when we wrote the recursive version, we saw that space complexity turned out to be order of n. And the reason for the space complexity was not any logical requirement of additional space, but the reason was recursive stack. What happened there? Whenever we made any recursive call, a new addition will be made to the stack. So in the recursive stack, more and more recursive calls are made, adding to additional space. So this is what caused order of an additional space. So when we convert this recursive solution to an iterative solution, we no more need the recursive stack. So when recursion stack is removed, your space complexity will come down to order of 1. So this is what we are going to achieve with the iterative algorithm for BST search. Okay. So let us try writing the iterative algorithm. In the algorithm, what is the logic we need? Whatever we already discussed in the last lecture, that whenever you reach a node, initially you will start from the root. You will check whether the value that you are searching for, let us say you are searching for value x. You will check whether x is the value in the root. If it is not, you will see whether x is smaller than root or if x is larger than root. If it is smaller, you have to go to the left subtree of the root and then continue the same operation in left subtree. If x is larger, you have to go to the right subtree of the root and then continue the same operation in right subtree. So because it is the same operation continued again and again, we used recursion. Let us try how to implement the same using iteration, because we know recursion and iteration are equal in power. So because of that, whenever you can write a recursive solution, you should also be able to write iterative solution. Let us start with the algorithm. Iterative BST search. This is the function that I want to write. BST search. So inside this function, what will be my input? One is root. So root will be root is the identity of any tree. Whenever you want to pass a tree to a function, you'll always provide the address of root. So root and let us say k. K is the value you are searching for in the tree. So what steps should you do? In case of recursive algorithm, we had a base case. So base case told us when to stop. Base case was whenever you reach a null value, you can stop by concluding that the searched element is not present in tree. If it is present in tree, then you will find that the key is equal to that value. So this null case was one among the base conditions. That is, if you hit that, you have to come out of recursion. In this case, we don't have a direct null case here because we only have one function, one call to this function. We won't be calling it again and again. So what we'll do is we'll write a while loop. So inside the while loop, we'll have a while loop. In the while loop, what should you have? You should first check whether the node is null. Then only you should enter this while loop. Node means root here. So what we'll do, if root, so if root means if root is not null, that is the meaning. If root is null, you can't do anything because there is nothing to be searched. If root is not null, there is something in the root. So you have some option to search. What will you do here? You have to first, there are three things to do. One, you have to check whether it is equal to the value. Then you have to check if it is less than, then it is greater than. So first we'll do if, let us say root pointing value. Root pointing value means whatever is the value in the root node. If that is equal to your key, if this is equal to key, what will you do? You can just return this root. Return root. Root means the node that you are presently in. What is the next step? In case this is not hit, then what should you do? If k is less than root pointing value. That means whatever you are searching for, if that value is lesser than whatever is present in root, what do you have to do? In case of recursive solution, you call the same function with root pointing left, meaning you would repeat the same in the left subtree. So here you are not going through recursion, you are iterating. So what should you do? You should change whatever is your present root. So root, this particular value should be changed to what? Root pointing left. You will change it to root pointing left. What happens now? Next iteration will be happening in left subtree. What is the next thing? Next step is you want to do the same search in right subtree. So if k, see, actually I can simply write an else case. I'm writing an if case so that, okay, it should be else if at least. Okay, I'm writing an else if case so that I can clearly show you what is the condition. When you are writing, you can simply write an else case here. If k is greater than root pointing value, then what happens? You should go to the right subtree. How will you go to right subtree? You should update root to root pointing right. Then you will go to the right subtree. So this is how you will go to right subtree. What happens if none of this is hit? That means there is no value. So this is the iterative algorithm for binary searching in a binary search tree. Here what are you doing? See, in this particular case, iterative algorithm looks quite simple, but the point is when you're dealing with trees, you generally go for recursive approach because that will be easier. In case recursive is difficult, in case iterative is difficult, recursive solution will be easier, but iterative will many times save space for you. So what did we do here? We checked whether root is available, the node, if there's some value in the node. If it is there, what did we do? We checked whether the value we are searching for is there in that node itself. If it is not, we'll check whether it is less than or greater than. If it is less than, you'll go to the right subtree. You'll continue this iteration with right subtree. And if it is greater than, what will you do? Sorry, if it is less than, you'll continue with left subtree. And if it is greater than, you will continue with the right subtree. So this is the algorithm that you should follow in order to, okay, what if this while is not hit? If this while is not hit, then you need to say that it is not found. So what will you do? You will return null. So null means the value is not present in this tree. That's what you're saying. So if it is not found, you will return null. If it is found, you will return whichever node is holding the value. If you come out of this while loop, that means you went through the tree and reached the point where there is no node, you reached a null node. So when you reach a null node, that means the value is not present in this binary search tree. So what is the time complexity? Time complexity is same as what we discussed previously, because here iteratively you are going from top of tree to the lower end of tree. So what is the maximum height possible for a binary search tree? Order of n. So time complexity is order of n. Space complexity here is order of 1 because there is no additional space used. So space complexity is order of 1. Additional space means constant space used is okay. You don't have space that increases with input value.